What if the universe isn't telling us the whole truth? We've been taught that nothing can move faster than light, that it's the ultimate speed limit built into the fabric of space and time. But some equations whisper otherwise. They suggest the existence of a particle so strange, so fast, it doesn't just outrun light, it may outrun causality itself. A particle that moves from the future into the past. We've never seen it, and yet it keeps showing up like a shadow just beyond the edge of reality. They call it the tachyon. And if it's real, then time, motion, and the structure of cause and effect begin to unravel. The universe has a speed limit. It's not written in a law book, etched in stone, or enforced by any cosmic patrol. And yet, it holds with a severity unmatched by anything we know. Light, the fastest thing we've ever known, moves through the vacuum of space at exactly 299,792,458 meters per second. Not a hair faster, not a moment sooner. It's a number so precise, so absolute, it anchors the architecture of reality itself. Time, space, causality, all kneel before it. But what if that limit wasn't a limit? What if something out there has already shattered it? For more than a century, physics has danced carefully around this question, eyes wide open, yet unwilling to stare directly at the implications. Because to do so is to invite chaos into order, to pull at the thread that holds cause before effect, to imagine a universe where something arrives before it even leaves. That's where the story of the tachyon begins. Not in discovery, not in detection, but in defiance. It was the early 20th century when Einstein laid down the principles of special relativity, the rules that declared nothing, not even information, can travel faster than light. And for decades, physicists respected that decree. They didn't question the light barrier. They worshipped it. To break it would unravel everything. And then came a whisper, a flicker in the mathematics, a ghost in the equations. A theoretical particle that, if it existed, would not just move faster than light. It must always move faster than light. It couldn't slow down. It couldn't join the subliminal world of protons and photons and people. It was born on the other side of the limit, a trespasser from a world we were never meant to see. They called it the tachyon. The name comes from the Greek word tachys, meaning swift, fitting, but almost understated. These weren't just fast particles. These were particles that reversed our understanding of motion, and not just motion, but time itself. You see, in relativity, the faster you go, the slower time flows for you. Near the speed of light, time nearly stands still. But if you were to go faster than light, just hypothetically, time would begin to flow backward. Not subjectively, not metaphorically, literally. Tachyons, if they exist, wouldn't just zip past us like cosmic bullets. They'd be moving from the future into the past, from outcomes into causes, like watching smoke curl into a cigarette, like hearing thunder before the lightning ever struck. But how does something like that even make sense? In truth, it doesn't, at least not in the world we inhabit. But physics isn't just the study of what is, it's the study of what could be, the space between observation and imagination. And sometimes our equations tell stories more haunting than any myth. Gerald Feinberg was the first to give tachyons a name and a voice. In 1967, he published a paper that examined their properties not as forbidden oddities, but as legitimate possibilities. He wondered aloud, in formal notation and careful logic, what it would mean if particles with imaginary mass could exist. Imaginary mass. That phrase alone is enough to spark unease. In mathematics, imaginary numbers are built on the square root of -1, a value that doesn't exist on the number line, yet is vital in everything from electronics to quantum theory. They're not fake. They're just sideways. They're orthogonal to our usual sense of scale. So what happens when mass, the property that resists acceleration, the thing that grounds you to the earth, becomes imaginary? The result is the tachyon. a particle that cannot be slowed down below the speed of light, one that gains speed as it loses energy, one that theoretically could never stand still, never stop, never decay in the way we understand. And if this sounds like science fiction, that's because it is. Tachyons have never been observed in a detector. No trail in a cloud chamber, no bump on a spectrum, no anomaly in a collider. And yet, they persist, because unlike unicorns or fire-breathing dragons, tachyons didn't come from folklore. They came from the deepest corners of our most trusted equations, not as artifacts of imagination, but as artifacts of symmetry, of completeness. They show up where theories extend themselves beyond the safety of certainty. They appear when you ask, what's on the other side of light? What happens if we don't stop at nothing can go faster? What if something already does? It's tempting to dismiss tachyons as a mathematical hiccup, a sign that we've pushed a model too far past the boundaries of reality. But sometimes, hiccups mean something. They're symptoms of something deeper, and this is where the mystery sharpens. Because in some versions of quantum field theory, tachyons appear not as real particles but as warnings, indications that a vacuum is unstable, that the ground we're standing on, the space we think is empty, is actually teetering on the edge of transformation. In that sense, the tachyon isn't a ghost, it's a shadow, a foreshadowing, a glimpse of what might be if the universe decides to rewrite the rules. But what if it already has? What if somewhere, in some corner of the cosmos or some layer of reality beneath the Planck scale, tachyons exist?
And if they do, what would they mean for us?
Not just as physicists or philosophers, but as inhabitants of time. Would they offer faster-than-light communication, travel through time, a new architecture of space itself? Or would they burn the concept of causality to the ground? Would they let us hear tomorrow's answers before we ask today's questions? We don't know. And that uncertainty, that trembling balance between what might be and what must not be, is precisely why tachyons remain one of the greatest unknowns in modern physics. They are not simply questions, they are questions that shouldn't exist. And yet, like whispers from the other side of the cosmic veil, they persist. Coming up next, we follow those whispers into the heart of paradox, where the line between cause and effect begins to blur, and tachyons stop being fast and start being terrifying. Causality. It's the one law older than physics itself, before E equals mc squared, before Newton's apple, even before fire and wheel and word. The idea that cause must precede effect, that time flows in one direction, is so deeply woven into our consciousness that we rarely question it. We don't need equations to prove it. We see it in falling dominoes, in ripples spreading from a stone, in the withering of leaves in autumn. It is not just a rule of the universe. It feels like the rule of existence. But tachyons suggest something different. They imply that this most sacred of sequences might not be universal, that in the hidden corridors of the cosmos, time could double back on itself, that somewhere, somehow, the effect might come before the cause. It's not a poetic flourish, it's the consequence of motion beyond light. Special relativity, the framework that governs how time and space relate at high speeds, does something peculiar when you dare to cross the light barrier. Time no longer behaves the same way. For observers in different reference frames, the sequence of events can shift. What is before for one observer may be after for another. As you push into superluminal speeds, this warping becomes more than just a quirk. It becomes a fracture. From certain perspectives, a tachyon emitted from a point in space might be seen arriving before it was ever released. To us, tethered to sublight intuition, that sounds impossible. But to the equations, it's just math. The implications are dizzying. Imagine a machine built with impossible precision that could emit a tachyon beam. If tachyons could carry information, even the faintest pulse, then in theory, a signal could be sent from the future into the past. You flip a switch, the machine hums, and before the process even completes, your past self receives the message. It sounds absurd, and yet the math doesn't forbid it. This has led to one of the strangest constructs in all of theoretical physics, the tachyon anti-telephone, a thought experiment so bizarre that even those who invented it felt uneasy about its existence. In it, two observers send messages to one another using tachyons, carefully coordinating reference frames and angles to produce a scenario where each message arrives before it was sent. The result? A closed causal loop. One where the message exists, not because it was authored, but because it was received. This is where reality begins to sweat. Because if such a thing were possible, we would be standing on a precipice, not just of faster-than-light travel, but of temporal collapse. A universe where the arrow of time bends in on itself, where the past can be rewritten from the future, where paradoxes aren't just science fiction, but logistical nightmares for the foundations of logic. And here lies the crux of the tachyon paradox. If they exist, why hasn't causality broken down already? Why don't we receive messages from tomorrow? Why hasn't someone in the future warned us of disasters we haven't yet seen? Why does time still behave like a river instead of a whirlpool? One answer, the conservative one, is that tachyons don't exist, that they're theoretical phantoms born from overextended models. Intriguing, yes, but ultimately fictional. But another possibility is more intriguing. Maybe tachyons do exist, but they can't be used to send signals. Maybe they can't interact with regular matter in the ways we need to shape information. Perhaps they slip through the universe like shadows behind a curtain, present, persistent, but unreachable. Maybe the laws of physics allow them to exist but not to communicate, a firewall around causality, a kind of cosmic censorship. Or perhaps, and this is where the air grows thin, the universe is far more self-correcting than we realize. Perhaps any attempt to construct a paradox using tachyons would fail, not because of technology, but because of something deeper, the architecture of probability itself. Some physicists have proposed the Novikov self-consistency principle, a mechanism by which time, even if looped or twisted, cannot produce contradictions. In this view, you could send information back in time, but only if doing so is consistent with what already happened. The past isn't mutable, it's inevitable. Even if you send a message to the past, it only ever causes what it caused all along. It's an eerie, fatalistic idea, one that implies we are not just passengers of time, but prisoners to its script. But there's something deeper still. Tachyons don't just raise questions about time. They raise questions about free will, about reality, about whether our experience of the present is the full picture, or just the surface tension of something deeper and more fluid beneath. Because if tachyons can violate causality, and if the universe still works, then maybe causality isn't as rigid as we think. Maybe what we call cause and effect is a local truth, not a cosmic one. Maybe time is not a line, it's a web, and we're tracing only one thread. It's here that the line between physics and philosophy begins to dissolve. We're no longer asking, can tachyons exist? We're asking, what would the universe have to be like if they did? And what does it say that it hasn't collapsed? Perhaps the answer lies not in the heavens, but in the equations, not in telescopes, but in thought. Because sometimes the most dangerous ideas aren't the ones we can prove. They're the ones we can't disprove, the ones that lurk just behind the edge of observation. And in the case of tachyons, what we find is not a creature of chaos, but a reflection, a mirror held up to time itself. So the question is no longer whether tachyons are real. The question is, what kind of universe would create them? And if the answer is this one, how would we ever know? Beyond the paradoxes and puzzles, something else is hiding, something quieter, something older. The math didn't just invent tachyons for fun. It summoned them for a reason. That reason begins to emerge in the trembling boundaries of quantum theory, where fields fluctuate, and where even empty space might not be so empty after all. The vacuum. We tend to think of it as nothingness, a hollow absence. a still silence between stars. But in the eyes of quantum field theory, the vacuum is anything but empty. It teems with energy. Virtual particles flicker in and out of existence, fields ripple with invisible motion, and what we call nothing is actually an ocean of potential. This is where tachyons begin to re-emerge, not as messengers from the future, but as indicators of instability. Shadows cast by a field on the verge of transformation. In quantum physics, particles are seen as excitations of underlying fields. The electron is a ripple in the electron field, the photon a ripple in the electromagnetic field. These fields pervade all of space, but sometimes their resting state isn't stable. Sometimes what looks like the lowest energy configuration is actually a false floor. And when that happens, something strange appears. A tachyon, not a particle exactly, but a signal, a mathematical flare that says, this vacuum isn't truly at rest. A tachyon in the equations doesn't mean there's a faster-than-light particle zooming through space. It means the field is poised to collapse, like a ball balanced at the top of a hill, pretending to be still. It's here that tachyons go from being science fiction to something eerily real. Not in the sense that we can catch them, but in the sense that they catch us. That they warn us when our theories are about to tip into something new. One of the most famous examples of this came with the birth of the Higgs mechanism. In early versions of electroweak theory, a tachyonic mass term appeared in the equations. It suggested instability, discomfort, a problem. But physicists didn't erase it. They embraced it. They realized that this problem was actually the seed of a solution, that the instability in the vacuum could cause spontaneous symmetry breaking, a shift in the field that would give rise to mass itself. The tachyon wasn't a flaw, it was a clue. This isn't unique. In many areas of theoretical physics, tachyon-like behavior hints that something deeper is waiting to be uncovered. A better vacuum, a more complete picture. In this way, tachyons have become something unexpected, agents of change. They are not real particles in the traditional sense. They are alarms. They are tensions in the fabric that demand resolution. But once that resolution occurs, once the field settles into a true vacuum, the tachyon disappears. What remains is structure, stability, the world as we know it. So in some ways, the tachyon is a midwife to reality, a necessary instability through which order is born. But still, the word tachyon holds on to that other meaning, the one that captivated so many minds, the idea of a faster-than-light traveler, of a particle that pierces the light barrier like a needle through silk. And here we find another problem, because while quantum fields can carry tachyonic modes, those modes don't behave like ordinary particles. They don't propagate. They don't carry energy the way photons or electrons do. They don't appear in detectors or leave trails in bubble chambers. They're not things so much as symptoms. This distinction matters because it means that when physicists say tachyon, they're often talking about something entirely different from what popular science has imagined. Not a spacecraft fuel, not a time machine component, but a warning flag in the landscape of equations. A signal that says, you're not at the true ground yet. Keep digging. And yet, that popular idea won't die. Because the notion of a particle that moves faster than light, that subverts causality, that exists in defiance of everything we've built our physics upon, it lingers, it seduces, it feels like a rebellion against the tyranny of limits. And perhaps that's why tachyons persist in culture, even as they retreat in science. They speak to something primal, the desire to outrun time, to escape the slow decay of cause and effect, to reach beyond. But science is careful. It doesn't give in easily to dreams. And in the realm of equations, every dream has a cost. That cost, in the case of tachyons, is imaginary mass. A concept that sounds like an oxymoron, but carries deep mathematical weight. In the relativistic energy-momentum relationship, mass appears under a square root. If that mass is imaginary, it inverts the relationship between energy and speed. As a tachyon loses energy, it gains speed, and if it somehow lost all its energy, its velocity would become infinite. That idea alone should make us pause, because it implies a particle that cannot rest. That becomes faster the closer it comes to emptiness. That reverses the laws of motion we take for granted. But here's the strangest part. The math doesn't explode. It continues to make sense. The imaginary mass doesn't break the theory, it just leads to behavior we've never seen in nature. And that's where the story slows, where it waits. Because for all our speculation, for all the mathematical allowances, the universe has yet to offer a single whisper of confirmation. Not one detected event, not one anomalous signal that couldn't be explained by something else. It's possible that tachyons, real, faster-than-light tachyons, don't exist, that they are artifacts of unfinished thoughts, ghosts that vanish when the final equation is written. But it's also possible that they do exist, that they move so fast, interact so weakly, or live in domains so remote we've simply never caught them. That they've been passing through us this whole time, like neutrinos on an even stranger leash. The truth is, we don't know. And in that uncertainty, the tachyon remains, not as a confirmed particle, but as a question, a mirror again, reflecting not what we see, but what we long to understand. And just as it vanishes from one theory, it appears in another, persisting, whispering, refusing to die. It's in the fabric of string theory that the whisper becomes a scream, because in that framework, a bold attempt to unite the universe's forces through vibrating strands, tachyons don't just show up, they demand to be heard. The promise of string theory was nothing less than everything: gravity, electromagnetism, the strong and weak nuclear forces, all woven together not as disparate parts of the cosmic machine, but as harmonious vibrations of tiny, one-dimensional strings. It was elegant, it was ambitious, it was beautiful, but it was not quiet. Because from the very first formulations, something strange stirred beneath the surface. A tachyon. Not an optional feature, not a side effect, a requirement. In the earliest versions of bosonic string theory, the equations insisted on a tachyonic mode, a state with imaginary mass, a built-in instability. This wasn't just inconvenient, it was catastrophic. Because in a theory that sought to describe everything, the fabric of reality, the essence of particles, the architecture of space-time, an instability wasn't just a flaw, it was a death sentence. It meant that the vacuum, the so-called ground state of the universe, wasn't stable. It meant that the universe, as described by this theory, was on the verge of collapse before it even began. To some, this was the end. A beautiful idea, ruined by a single ghost in the math. But to others, it was the beginning of a deeper truth. Physicists didn't run from the tachyon, they stared it down. And what they found wasn't destruction, it was evolution. In time, new versions of string theory emerged, supersymmetric extensions where tachyons were banished. These theories were more stable, more consistent, more safe. And yet, even in those new frameworks, the memory of the tachyon lingered. It had done something important. It had forced the theory to grow, to confront the difference between what is mathematically allowed and what is physically real. Because the tachyon in this case wasn't just an error, it was a signal. It said, you've made a universe, but it's not ready yet. And so string theory adjusted. It added symmetry, it added dimensions, it folded in new layers of complexity, not to erase the tachyon, but to absorb its warning. In some formulations, the tachyon became a kind of transition state, a marker of a decaying vacuum. In others, it represented a field rolling toward a new equilibrium, a more stable geometry of space-time itself. And then came brains, higher dimensional objects that strings could attach to. Tachyons emerged again, this time in the context of unstable brain configurations. When brains collided or overlapped in certain ways, tachyonic modes appeared. Once again, instability reared its head, but instead of rejection, physicists saw opportunity. Maybe the decay of these brain configurations, driven by tachyon condensation, could help explain why our universe looks the way it does, why it has 3 large spatial dimensions and not 10, why it has the structure we observe and not chaos. The tachyon, again, wasn't the enemy, it was the sculptor. What began as a flaw became a feature. What looked like a problem became a mechanism for shaping the early universe, for driving transitions between vacua, for understanding how something coherent could emerge from something broken. This is a recurring theme in physics. The universe doesn't hand us neat answers. It hands us inconsistencies, paradoxes, things that shouldn't be but are, and often it's those very contradictions that lead us forward. Tachyons are perhaps the purest expression of this, because they are, by their very nature, contradictions. They don't fit, they don't behave, they break the rules of motion, of time, of causality. And yet they keep returning, in new theories, in new forms. Each time they tell us that our understanding isn't wrong, it's incomplete. It's tempting to think of physics as a finished puzzle, that with enough pieces the picture will appear. But sometimes the pieces shift, the edges blur, and a shape you thought didn't belong turns out to be the key. Tachyons do that. They don't just challenge our understanding of particles, they challenge our understanding of understanding. They ask, what is real? Is it what we can see, measure, detect? Or is it what the equations demand, even if we can't yet reach it? In string theory, the presence of tachyons told us something vital, that not all vacuums are created equal, that not all configurations of energy and geometry are safe, some are temporary, some are fated to fall apart. And maybe, just maybe, our own universe passed through such a stage. Perhaps the early cosmos was seeded with tachyonic fields, unstable, trembling with potential, rolling down a cosmic hill toward a valley of order. Maybe the Big Bang wasn't a single spark, but a transition from an unstable phase to a stable one. In that view, tachyons were not mistakes. They were the beginning of the story, a story where decay gives birth to structure, where instability gives rise to the laws of nature, where what breaks also builds. But not everyone is satisfied with metaphors. Some still ask, what if tachyons really are particles? What if there's a kind of matter that travels faster than light, not as a mathematical warning, but as a physical entity? What if these weren't fields decaying or strings vibrating, but particles soaring, always faster, always unreachable? It's a dangerous thought. Because if you open the door to faster-than-light particles, you don't just open it for one, you open it for everything they imply. Time travel, causality violations, energy instabilities. The collapse of the very foundation physics stands on, and yet the door remains ajar, because for all our efforts we've never proven that tachyons cannot exist, only that they haven't yet shown themselves, and so they remain at the fringe, not quite myth, not quite fact, a whisper in the strings of reality. And somewhere beyond that whisper, in the gray zone between theory and experiment, lies the next question. If nothing can go faster than light, why do some things seem to? Why does the universe sometimes behave like it forgot its own rules? And could that be where tachyons hide, not in what is, but in what seems to be? The universe has always had a way of showing us things we weren't ready to believe. Stars that pulse with the precision of atomic clocks, particles that exist in 2 places at once, forces that act across a vacuum as if empty space were a lie. And then there are those phenomena, stranger still, that seem to mock our most sacred rule, that nothing can move faster than light. Because sometimes it looks like something does. It's an illusion, they say, a trick of the math, a misreading of what's real, and yet the evidence is there, lurking in the margins of quantum mechanics and wave theory, whispers of velocity where none should be. Take, for instance, quantum tunneling. A particle approaches a barrier it shouldn't be able to cross, not without enough energy, not without breaking the laws of classical physics, and yet, somehow, it appears on the other side, instantly, as if the barrier were never there, as if the particle decided it simply didn't have time for walls. When physicists first studied the speed at which this tunneling seemed to occur, they found something strange. It didn't just beat expectations, it beat light. The particle's wave function didn't slow down through the barrier. In some models it appeared to accelerate, to emerge sooner than it should. The deeper the barrier, the quicker it exited. It defied logic. It demanded explanation.
And the explanation, as always, came with caveats. The particle itself never truly exceeded the speed of light. The speed in question referred to the phase of the wave function, not the transmission of energy or information. No causality was violated, no tachyons were summoned.
But the implication remained. Something had moved through faster than expected, and the only thing stopping us from calling it superluminal was caution. The same goes for phase velocity, a property of waveforms where the peaks of a wave can appear to move faster than light. It doesn't carry information, it doesn't transmit energy. It's not real in the conventional sense, but it looks real. And sometimes, appearance is enough to stir questions. What if these aren't just quirks of equations? What if they're footprints? What if tachyons, in whatever form they may take, are hiding in these ambiguities, surfing on the margins of wave mechanics, slipping past the light barrier not as particles, but as distortions? It's a possibility that haunts the fringes of theoretical physics, because while we cling to the certainty that no object with real mass can accelerate to the speed of light, nothing in the laws of physics forbids something from starting beyond it. That's where tachyons live, in that loophole. They don't break the rules, they exist outside their jurisdiction, and yet, for all the loopholes and illusions, for all the strange results and faster-than-light appearances, there remains a single problem: detection. If tachyons exist, why can't we find them? Why don't they crash into detectors, leave trails of destruction, glimmer in data the way neutrinos or cosmic rays do? The answer, again, may lie in their nature, because tachyons aren't just fast. They're anti-interactive. The faster they go, the less energy they carry, the less they disturb the world around them. Where a normal particle gets heavier as it accelerates, a tachyon gets lighter. Where normal matter becomes harder to move, tachyons become impossible to slow down. They don't deposit energy, they avoid interaction. It's like trying to catch a shadow with a net. Some theories suggest that if tachyons were real, they would have already passed through the Earth countless times, unseen, unfelt, unmeasured. And even if one did manage to leave a trace, it might not look like anything we recognize. It could mimic noise or vanish before its presence is known. There have been searches, of course, experiments combing through data from particle accelerators, cosmic ray observatories, and deep underground neutrino detectors, all hunting for anomalies, all hoping to catch something, anything, that might hint at a particle outrunning light. But so far, the silence is deafening. And yet, even silence can speak. It tells us something about the nature of the tachyon. Not that it's fiction, but that it belongs to a different class of reality. Perhaps one that doesn't overlap with ours, or one that does, but only in ways we haven't yet learned to see. That's the burden of looking for things at the edge of possibility. Sometimes the very nature of what you're seeking is that it cannot be seen. Like black holes before Hawking radiation, like dark energy before cosmic acceleration, like atoms before the microscope. Absence isn't disproof, it's an invitation to think differently, to look deeper, to expand the very notion of what's observable. And in that expansion, we begin to glimpse something extraordinary. That tachyons, real or not, are more than particles, they're tests. Tests of how far we're willing to stretch our imagination. Tests of how much uncertainty we're willing to entertain. Tests of what we believe the universe is allowed to do. Because sometimes the most disruptive truths are the ones we keep just out of reach, the ones we suspect but cannot confirm, the ones that refuse to collapse under observation. So we keep looking, in the tunneling of electrons, in the shimmer of cosmic rays, in the symmetries of broken fields, in the places where time and space tremble just slightly out of sync. And in those places we find the suggestion, not proof, not evidence, but suggestion that perhaps light is not alone, that somewhere out there something moves faster, not in defiance, but in silence. Not to be seen, but to be felt in the uncertainty it leaves behind. And maybe that's the point. Maybe the tachyon isn't something we'll ever hold in our hands or see on a graph. Maybe it exists to remind us that the limits of knowledge are not the limits of reality. And if so, we're left with the most uncomfortable question yet. What happens if the universe is hiding something on purpose? Every so often, the universe whispers through equations. It doesn't shout. It doesn't flash a signal in the sky. It simply leaves something behind. A trace in the math, like footprints in snow. The kind you almost miss, unless you're looking closely. And for those willing to look, something peculiar begins to emerge. Tachyons, for all their ghostly strangeness, aren't just a one-time glitch. They're recurring, persistent, like a word you've never heard before suddenly appearing everywhere. They don't just show up in one theory. They haunt the foundations of many. In this sense, they are not particles, they are symptoms, indicators that a theory, as elegant as it might seem, is incomplete, or that it's sitting in the wrong vacuum, balancing atop a false minimum, destined to fall. In field theory, their appearance is often a red flag, a sign that the model you've constructed, the framework you trust, contains an instability, something that will eventually break or roll into something new. It's like hearing a crack in the ice beneath your feet. You may still be standing, but not for long. But the deeper mystery lies in this. Why do they keep showing up at all? Why does the math, again and again, insist on producing these phantom terms, fields with imaginary mass, solutions that exist only at velocities above light speed? It's not just coincidence, it's something structural, something fundamental. Take the Klein-Gordon equation, a foundational tool in quantum field theory. It's a relativistic equation meant to describe spin-zero particles. Simple, clean, respected. And yet, even here, if you tweak the mass term just slightly, give it a negative square, you get a tachyon. Not because the math broke, but because it allowed it. It's as if, buried within the logic of space-time itself, there's a hidden symmetry, a counterbalance, a kind of mirror image of what we know moving in reverse. As though every law that governs our world has an inverted twin, unseen, untouchable, but mathematically real. The idea isn't new. In physics, symmetry is everything. We see it in conservation laws, in force unification, in the deep connection between space and time, energy and momentum. And often, when a symmetry is broken, something is born. Mass, force carriers, even the universe itself. Could tachyons represent a symmetry we don't yet understand? Not just an instability, but a reflection of a reality we haven't accessed. Some have speculated that tachyons are simply the other side of the cosmic coin. If normal matter exists in the subluminal regime, always below the speed of light, then tachyons might exist in a separate realm, a superluminal sector, forever beyond our reach. In this view, they are not invaders from the future or errors in our code. They are a different class of being entirely, bound by their own rules, their own constraints. To us, time flows forward. To them, it flows differently, perhaps backward, perhaps sideways, perhaps in circles. It's not just speculative, it's deeply unsettling, because if such a mirror sector exists, it may be fully formed, fully real, and yet utterly invisible. A universe of particles and fields that never interact with ours in meaningful ways. A shadow realm defined not by darkness, but by disconnection. And here, the nature of reality begins to warp. Because if math allows it, if symmetry permits it, can we really say it doesn't exist? It's tempting to say yes, to invoke Occam's razor, to prune away the parts of the theory that don't yield results. But physics has burned its hand on that razor before. Once, it seemed ridiculous to speak of particles that could pass through miles of lead without interacting. But neutrinos exist. Once it seemed absurd to suggest that space could expand faster than the speed of light. But inflation happened. Once it was believed that the atom was indivisible. That time was absolute. That space was static. We were wrong. Not because we lacked imagination, but because reality lacks obligation. It is not bound to be intuitive. It is not shaped by what we can easily measure. It is shaped by consistency, logic, and, more than anything, by mathematical necessity. And here's the uncomfortable truth. The math doesn't banish tachyons. It embraces them, quietly, reluctantly, but undeniably. They show up in attempts to unify gravity with quantum mechanics. They appear in extended field theories, in modifications of general relativity, in models that test the boundaries of what's knowable. They haunt the margins of every grand theory, like static on an old radio, always present, always just out of reach. And yet, despite their persistence, they leave no trace in the lab. We've looked for anomalies in particle decays, for unexplained signatures in high-energy collisions, for trails in Cherenkov detectors, those glowing cones of light that show when something moves faster than light in a medium. Nothing, at least nothing we're ready to accept. And perhaps that's the point. Perhaps tachyons can't be detected because they're not meant to be. Because they are, by their very definition, untouchable. Not in a mystical sense, but in a structural one. Built into the architecture of the cosmos in such a way that their presence can only ever be inferred, never confirmed. That's what makes them dangerous. Not because they break the laws of physics, but because they don't. They fit too well. They're too clean, too consistent. Like a shape in the fog that never quite resolves, but never quite fades either. So we watch, we calculate, we write and revise, and the math continues to whisper. The tachyon is not gone, it's not disproven, it's simply waiting for a new context, a new theory, a new kind of eye. And when that day comes, if it comes, we may find that what we thought was a ghost in the system was something far more profound. Not an intruder, but a foundation we never knew was missing. There's a strange kind of beauty in broken symmetry. A snowflake split by warmth, a perfect pattern shattered to reveal something new. In physics, symmetry is power, but the breaking of it, that's where the universe begins to breathe. The story of mass, the weight of everything we know, begins not with atoms or molecules or even energy, but with a broken symmetry. A field stretched across the fabric of space-time, lying silent and invisible until one day it shifted. This field is called the Higgs field, and through it the particles of the Standard Model gain their mass. Not because the particles changed, but because the environment did. They moved through a medium that resisted them. That's what mass is in this view, resistance to motion through an invisible field. But rewind that story just slightly. Back to the early models, the primitive attempts to unify the weak force and electromagnetism into something coherent. There, at the heart of the mechanism, was a tachyon, not a particle in the usual sense, but a placeholder, a signature of something being not quite right. The Higgs field, before it settled into its lowest energy state, was unstable, and in that instability, the equations yielded a mass term that wasn't just negative, it was imaginary. A tachyonic mass. To some, it looked like a failure. The theory predicted a particle that shouldn't exist, a ghost that traveled faster than light, something that broke causality, but others looked deeper. What if the tachyon wasn't a failure, but a signal? What if it was telling us that the vacuum, the baseline of reality itself, was in the wrong place? This insight became the cornerstone of spontaneous symmetry breaking. The tachyonic mass didn't mean a faster-than-light particle was flying around the cosmos. It meant that the field was on unstable footing, ready to roll down an energy hill to a stable state. A true vacuum, a universe with mass. So the tachyon didn't vanish. It transformed. It gave way to a new ground state, a new configuration. And in that transformation, the universe gained structure. Electroweak symmetry split, and the W and Z bosons became massive, while the photon remained massless. The scaffolding of the world snapped into place. The particle once described by the imaginary mass term didn't remain a tachyon. It became the Higgs boson, the long-sought keystone of the Standard Model, finally discovered at CERN in 2012. And in that moment, the tachyonic whisper that had haunted the equations for decades was finally understood. It was never a particle at all. It was a phase transition, a flicker between two realities. This kind of shift isn't unique to high-energy physics. We see echoes of it in everyday life. Water freezing into ice, iron becoming magnetized. These are changes in state, new order arising from old instability. And the mathematics that describes them often passes through a similar terrain: unstable points, imaginary values, transient forms that exist only in the moment of change. Tachyons, in this light, are not violations of reality. They are expressions of its dynamism. They show us that the universe isn't static. It evolves, it self-corrects, it reshapes its own vacuum when necessary. This idea of fields shifting, of vacuums changing, has implications far beyond the Higgs. It opens doors to questions about the early universe, the nature of dark energy, and the possibility of multiple vacua. That our current universe might not be in its true ground state, but resting in a false one, stable for now, but destined to decay. And what would mark the beginning of such a decay? A tachyon, the same mathematical flare that signaled instability before, could one day reappear, not as a particle, but as a prelude. A sign that reality itself is about to shift again. This isn't science fiction. It's baked into many models of cosmology and quantum gravity. The idea that our vacuum might be metastable, that a lower energy state exists somewhere, unreachable for now, but not forever. And if a bubble of that true vacuum were to nucleate, it could expand at nearly the speed of light, rewriting the laws of physics as it swallowed everything. Time, space, matter, all recalibrated, all reborn. The tachyon in that terrifying moment would not be the destroyer, it would be the herald. The universe would not end in fire or ice, but in a shift, a recalculation, a falling through the floor we never knew was false. But until that moment, if it ever comes, we remain here, suspended in a vacuum that appears stable, surrounded by particles that move below the speed of light, bound by constants that seem eternal. And yet, the story of the Higgs reminds us, nothing is truly fixed, not even the vacuum, especially not the vacuum. The tachyon was not a mistake in the equations, it was the invitation to a deeper truth, a door hidden behind what seemed like an error. And that may be its most powerful role of all, because it forces us to ask, how many other so-called mistakes in our theories are actually messages? How many ghosts in the machine are not glitches, but guides? Every time a tachyon appears, it tells us that we've built something that can evolve, something that's teetering on the edge of change, and every time it disappears, it's not erased, it's fulfilled. This isn't just the story of mass. It's the story of how physics dreams forward, how the math outpaces the instruments, how the shadows form before the shapes. And it raises a question too vast to ignore. If a tachyon gave birth to the Higgs, what else might they be trying to create? What other shifts, what other transitions wait in the quantum fog just ahead? Because the universe is still whispering, and the tachyons, it seems, have not yet said their final word. The deeper we go into the architecture of the universe, the less solid it becomes. What we once thought of as particles become vibrations. What we believe to be forces become fields. And what we imagined as emptiness reveals itself to be pregnant with possibilities. String theory didn't begin as a theory of everything. It began as an accident, a mathematical attempt to explain the strong nuclear force using vibrating strings rather than point-like particles. But the theory quickly grew, too large, too elegant, too compelling to be confined. It suggested that everything in the universe, matter, energy, gravity itself, might be the result of tiny, one-dimensional strings vibrating in a multi-dimensional space far beyond human perception. Each vibration gave rise to a different particle, a different property, a different force. It was bold, ambitious, almost romantic, and from the very beginning, it was haunted. Because in the earliest versions of string theory, the so-called bosonic string theory, a tachyon appeared at the ground level, not in some fringe corner, not as an optional term, but at the very core of the theory's spectrum. It was unavoidable. The tachyon mode showed up as the lowest energy state of the bosonic string, an instability at the very foundation of the universe the theory described. To most physicists, this was not just a red flag, it was a fatal flaw. How could a theory meant to unify all of physics be built upon an unstable vacuum? A tachyonic state meant that the ground state wasn't truly a minimum. It meant that the universe, as described by the theory, would immediately collapse into something else. It couldn't last, it couldn't even begin, but not everyone turned away. Because some looked at the tachyon not as a sign of failure, but as an opportunity. If the vacuum is unstable, they reasoned, then maybe we're simply not in the final version of the theory yet. Maybe the tachyon isn't a dead end, but a transition, a map to a more stable formulation. This led to the development of tachyon condensation, the idea that the presence of a tachyon indicates that the system will evolve into a new vacuum, one that no longer contains the instability. The tachyon disappears not because it was an error, but because its job was done. In this way, the presence of a tachyon wasn't just tolerated, it was necessary, a mechanism for theoretical evolution. It's a curious role reversal. The particle that once seemed to break the rules became the path to order. But the cost of keeping the theory intact was high. Bosonic string theory was limited. It had no fermions, no supersymmetry, no obvious connection to the known particles of the standard model. So theorists went further. They developed superstring theory, a richer, more complex framework that incorporated supersymmetry, paired every boson with a fermion, and crucially, removed the tachyon from the ground state. In these newer theories, stability was achieved. The ghosts were exorcised. The vacuum no longer trembled. And yet, even in these stable formulations, the idea of tachyons never quite left. Because in the study of D-branes, extended objects in string theory that strings can attach to, tachyonic modes still emerge. When two D-branes intersect or lie too close in the wrong configuration, the system becomes unstable. A tachyon appears, not as a problem, but as an indicator that the branes are not in a stable arrangement. And once again, the tachyon becomes a messenger, a signal that the configuration will decay into something new, perhaps a lower dimensional brane, perhaps a different vacuum, perhaps nothing at all. Tachyons, in this sense, are like gravitational murmurs. They tell us that something is moving, evolving, reconfiguring behind the veil. And more than that, they tell us that the universe may not be static, even in its most foundational layers. That the vacuum, the thing we so often take for granted as stillness, might be in flux. That what we experience as permanence might be temporary. In this framework, the tachyon is not simply a theoretical nuisance or a hypothetical particle. It is a transformer, a bridge between vacua, a mechanism through which the universe reshapes its own foundation. Some have even suggested that the decay of unstable brane configurations through tachyon condensation might explain why our universe has 3 large spatial dimensions instead of 10. In a sense, the shape of reality itself may have been sculpted by the decay of tachyonic states. It's humbling. and a little terrifying. Because it means that the stability we see, the constants we measure, the laws we rely on, may be the ashes of an earlier instability. That our cosmos, ordered as it seems, might owe its coherence to a history of collapse. And this isn't ancient history. In the deep past of the universe, moments after the Big Bang, these processes may have played out. Tachyonic instabilities may have sculpted the energy landscape, shaped the fields, selected the dimensions that would endure. We don't observe these transitions. We live in their aftermath. We are the children of a cosmic resolution. And the tachyon, though gone, remains in the background, a signature, a scar in the equations. A reminder that even the most sacred truths may one day give way. Because if tachyons are real in any meaningful sense, they are not just phenomena, they are forces of change. And that makes them dangerous. Not because they defy physics, but because they demand more of it. They insist that the vacuum itself is a question, not an answer. That symmetry, while beautiful, is never eternal. And that even the most stable theories may someday fall. Perhaps that's the lesson the tachyon came to teach. That even in our most precise formulations, the seeds of instability are always present. That nothing, no theory, no vacuum, no universe, is beyond transformation. And if we accept that, then a deeper question emerges, one that echoes into the farthest reaches of physics. What else is waiting to change? The speed of light, immutable, unyielding, etched into the foundation of reality like sacred law. It is the one barrier we have never crossed, not in experiment, not in spacecraft, not in dreams that wish to stay tethered to physics. Every particle, every signal, every whisper of energy that moves through our universe is caught in its grip. Not even light itself outruns it, because, by definition, it is light. But just beyond that shimmering threshold lies speculation. A world not forbidden by the laws of physics, but sealed off by them. Not because it is wrong, but because it is unreachable. And yet, like all forbidden places, we are drawn to it. We peer across the boundary and wonder, what if something lives there? Tachyons, if they exist at all, live not in our realm, but in that one, a domain where faster-than-light motion is not just possible, but required. And here's the twist that makes tachyons so strange. They don't start below the speed limit and try to break it. They're born beyond it. They can't slow down to light speed. It's as forbidden to them as exceeding it is to us. They exist on the far side of the mirror. And if you attempt to chase one, if you try to accelerate to catch up, it only races farther ahead. In fact, as it loses energy, it moves faster. As it approaches zero energy, its speed grows toward infinity. This isn't how any other particle behaves. For ordinary matter, the closer you push it toward light speed, the more energy it takes. Each inch closer costs exponentially more. You need infinite energy to reach that barrier. But tachyons? They're accelerating in the opposite direction. Their infinite velocity lies not in the future, but at the edge of vanishing. A particle that grows faster as it fades. And this leads us to a terrifying implication. What if there is a class of reality that's accelerating away from us, not in space, but in velocity, so fast, so untouchable, that we could never slow it enough to make contact? It's not that tachyons refuse to be seen. It's that we exist in different light cones. In the framework of special relativity, every object's motion is confined to a light cone, a diagram that maps out all possible paths through space-time, given the speed of light as a limit. Ordinary matter stays within the cone, light rides its edge. But tachyons exist outside the cone. Their paths through space-time do not intersect ours in the usual way. We cannot send signals to them. They cannot send messages to us, not in any frame where causality remains intact. It's not communication, it's a wall of silence. And yet, we find echoes, hints, paradoxes. The idea of faster-than-light particles has always hovered just outside the realm of acceptability. And in our efforts to understand whether such things could ever be real, Physicists have dug into the loopholes of nature, places where light speed seems to lose its authority. There are phenomena that appear to move faster than light. Phase velocities in waves, interference patterns sweeping across surfaces. Even shadows, cast by distant objects, can move across the moon at speeds faster than c. But none of these carry energy, none of them move matter. They are illusions of motion, like a laser dot racing across a wall. They break no rules because they are not truly moving. They're artifacts of geometry, of perspective. Still, the idea persists, because the question remains unresolved. Can the universe hide faster-than-light motion behind a veil of non-interaction? Could tachyons be more like fields than particles? Subtle ripples in the structure of space that don't leave a trace unless something shifts. One idea proposes that tachyons might mediate interactions across causally disconnected regions of the universe, not as messengers, but as structural bridges, not transmitting information, but structuring possibility. Others suggest they could have existed only in the early moments of the universe, when the vacuum itself was chaotic and malleable. That in those first microseconds after the Big Bang, faster-than-light fields may have dictated the unfolding of space-time, and when the dust settled, they disappeared, or went dark. Perhaps we don't see tachyons now, because their job is done. Or maybe they persist, but only as unobservable consequences. There's an eerie symmetry in that thought, that the things which shaped our universe might no longer be part of it, that the architects were never meant to stay, that the scaffolding fell away the moment the structure took hold. This idea isn't unique to tachyons. We've seen it before in physics. Symmetry breaking, vacuum transitions, inflation fields, powerful forces that act only in the beginning, and then vanish. But tachyons differ in one haunting way. They're still in the equations. We don't just remember them as historical curiosities. They continue to appear, quietly, persistently, in models, in transitions, in edge cases that we don't quite understand. As if the universe itself isn't quite finished with them. And this raises a possibility more unsettling than any violation of causality or mass. What if tachyons exist not as entities, but as evidence? Evidence of a deeper layer of physics, a speed-based symmetry, a dual sector of particles and fields we'll never touch, but whose presence shaped everything we know. Not signals, not intruders, foundations. And if that's true, then we may already be surrounded by tachyons, not flying through us like bullets, but resting beneath the very laws we believe are fixed. A quiet influence, a ghost framework, the faster-than-light backbone of a slower-than-light world. What we experience as mass, motion, and causality may be the surface tension atop a sea of unseen motion. And if we could dive below that surface, what else might we find? Not just particles faster than light, but ideas faster than understanding. The next part of this story isn't about motion, it's about the silence, the absence, the problem that remains after all the detectors go quiet. Why haven't we found a single tachyon? Why, in all the noise of the universe, do they leave no trace at all? We've built machines that collide particles at nearly the speed of light. We've drilled into mountains to listen for neutrinos. We've launched telescopes into orbit to stare across billions of light years. And with each layer of effort, one question becomes harder to ignore. Why haven't we found a single tachyon? For a particle so deeply rooted in theory, so persistent in the margins of our most sacred equations, its absence feels pointed, not just unexplained, but deliberate. A silence so absolute, it starts to resemble design. If tachyons exist, why don't they leave evidence? Why don't they flash through detectors, crash into nuclei, or ripple through space-time the way all other particles do? The simplest answer is that they don't exist. That tachyons are mathematical ghosts, figments of unstable fields, scaffolds for theories not yet complete. That once the math is cleaned, the ghosts disappear. But what if it's not that simple? What if tachyons are real, but not observable in any way we currently understand? The problem begins with interaction. Tachyons, by their very nature, would be utterly unlike any known particle. They don't slow down, they don't follow light speed limitations, and perhaps most critically, they may not interact with ordinary matter at all. Imagine something that moves faster than light, but as it gains speed, loses energy. In fact, the closer it gets to infinite speed, the less it interacts with the universe. It becomes invisible, not because it's hidden, but because it slips through reality like wind through a net. This idea isn't just poetic, it's embedded in the mathematics. Tachyons, if described as field excitations, would have imaginary mass. Their energy would be fundamentally complex. The moment you try to plug them into a framework built on measurement and detection, they resist. They don't produce the right signals. They don't light up the right instruments. They're structurally unobservable. Some theories have proposed that if a tachyon were to interact with a detector, it might emit Cherenkov radiation in reverse, the blue glow we observe when a charged particle moves faster than light in a medium. But tachyons would be too fast even for that. They wouldn't decelerate, they wouldn't deposit energy, they would pass through the field indifferent, like trying to shake hands with a shadow. Detectors are built to catch things that interact: photons, electrons, muons, even elusive neutrinos. But tachyons are, in every sense, antisocial. And so we wait for a signal that may never come. We scan the skies, watching for anomalies in cosmic rays, energetic particles from distant galaxies that crash into our atmosphere at near light speed. We monitor neutrino observatories, looking for unexplained blips, particles that arrive too early or behave too strangely. So far nothing, and still, the idea refuses to die. Because sometimes nothing is the loudest signal of all. In science, absence is a form of presence. A failed experiment is still a data point. An unanswered question is still a direction. And the failure to find tachyons is not a door closed. It's a hallway we haven't finished walking. We've been here before. The neutrino was first predicted by Wolfgang Pauli not because it was seen, but because it had to exist, to account for missing energy in beta decay. For decades, it remained invisible, undetectable, ghost-like, until we built detectors sensitive enough to confirm its existence. Tachyons, if they're anything like neutrinos, may require not just new instruments, but a new kind of thinking. Perhaps they're not individual particles, but disturbances in a deeper structure. Perhaps they can't be detected directly because they don't manifest until a theory breaks down. Their presence might be conditional, like a warning light that only turns on when you've reached the limits of your model. Or perhaps the question of detection itself is wrong. Maybe tachyons aren't meant to be found. Maybe they are mathematical inevitabilities like negative numbers or imaginary units, not physical objects, but essential tools. There was a time when the square root of -1 was considered nonsense, an absurdity. And yet today, imaginary numbers are indispensable to physics, engineering, quantum mechanics. They are not real in the conventional sense, but they describe reality with unmatched precision. Tachyons might belong to this same category, things that don't exist in isolation, but are necessary inside the machinery of the universe. And yet the desire to prove them persists, because a confirmed tachyon, real, observable, measurable, would change everything. It would shatter the speed limit, open new windows into causality, demand a rewriting of relativity, perhaps even hint at hidden sectors, alternate timelines, or entirely new geometries of space and time. The cost would be enormous, but so would the reward. And in that possibility, physicists continue to search, not because they expect to find, but because the not finding still tells us something. It tells us where our limits are, what our theories can explain and what they can't, what we can measure and what we can only suspect. And in the shadow of that silence, the question deepens. Not where are the tachyons, but what does it mean that we haven't found them? That in all our machines, all our colliders and cosmic monitors, all our equations and models and mirrors pointed at the stars, they leave no footprint, no echo, no scar, not a trace. It is a mystery that loops back on itself, and like all good mysteries, it leads to another question, one that's been hiding at the edges of this entire pursuit. If tachyons are not particles, what are they? A warning, a mirage, a metaphor, or something else entirely? Perhaps to answer that, we need to stop asking whether tachyons are real and start asking what it means to be real in a universe where the invisible builds the visible and silence can speak louder than any particle. There are some ideas in physics that seem to outlive their own relevance. They linger, not because they are proven, but because they refuse to be forgotten. They're not discarded when disproven. They're folded into the deeper conversation, kept alive as metaphors, tools, provocations. Tachyons are one of those ideas. Not quite banished, not quite embraced, suspended in the space between metaphor and math, like a riddle whose answer remains just out of reach. And perhaps that's because they serve a role we rarely talk about in science. They ask better questions than they answer. In this sense, the tachyon is not a particle at all. It is a philosopher's particle, a thing that exists not to be detected, but to be considered. A theoretical device, engineered not to reveal itself, but to illuminate the boundaries of what we think we know. It's easy to mistake physics for certainty. Equations with equal signs, constants that stretch across galaxies, predictions that land with pinpoint accuracy. But underneath all that precision lies something messier, older, and more human, a profound discomfort with the unknown. And the tachyon is a mirror held up to that discomfort. It forces us to confront the assumptions we don't even know we're making. It reveals where our models are fragile, where causality gets fuzzy, where time, that relentless arrow we take for granted, begins to curve in ways we can't quite follow. It asks, what does it mean for something to move faster than light, when light defines what motion even is? What does it mean for mass to be imaginary, when our entire concept of substance is grounded in mass? What does it mean to exist outside the light cone, when the light cone is our definition of existence?
These aren't just mathematical questions, they're ontological. They strike at the roots of reality and at the limits of language itself.
Because if you accept tachyons, even as thought experiments, you must accept that your intuitions about cause and effect, about motion and time, are incomplete. That the universe may be more than it seems, not just in size or scale, but in kind. And this perhaps is the true function of the tachyon, to guard the threshold of the unknowable, to sit at the edge of understanding like a sentinel, reminding us that not every theory ends in confirmation, some end in transformation. We've seen this before. The ether, once believed to be the invisible medium through which light waves traveled, it was never detected. Eventually, it was discarded. But in trying to prove the ether, physicists discovered something else, the invariance of the speed of light, the foundation of special relativity. The ether didn't survive, but it led to the theory that replaced it. Tachyons may serve the same purpose, not as real entities, but as conceptual catalysts, forcing us to build stronger, more complete models in order to explain why they can't exist, or why they must. They create tension, and from that tension, we refine our understanding. In this way, tachyons are deeply useful, not because they are real, but because they won't go away. They persist in equations. They reappear in revised models. They haunt the back halls of quantum field theory, string theory, cosmology, and they refuse to offer closure. Even their name, tachyon, is a kind of open wound, a placeholder for a thing we suspect might be missing, a speed we'll never reach, a boundary we'll never cross. And yet, we need them. Because physics is not just the study of what's known, it's the study of what's knowable. And tachyons sit on the other side of that boundary, whispering that the map isn't finished, that there are lands still undiscovered, perhaps undiscoverable, but no less real for it. There's a kind of humility in that, a recognition that the universe is not obliged to be understood, that its rules may not be universal, that its truths may not be symmetrical, elegant, or even observable. Tachyons remind us that science is not a monument, it is a process, a conversation with the unknown. They embody the spirit of inquiry, not the clean, orderly kind, but the restless, relentless kind. The kind that admits ignorance, confronts paradox, and walks toward the darkness anyway. This is not weakness, it is strength, to build entire theories around particles that may never exist, to chase ideas that may never pay off, to question even the laws that seem immutable. It's how we move forward. And if tachyons turn out to be nothing more than an artifact, an echo of a flawed equation, or an unstable vacuum, then they will still have done their job. Because in trying to understand them, we were forced to understand ourselves, our need for limits, our reverence for light, our terror of what lies beyond causality, and our quiet, aching hope that there's something out there we haven't seen yet, something stranger, something faster, something that moves not just through space, but through the limits of imagination itself. In the end, whether tachyons exist may matter less than the fact that we keep asking. And in that question, in its persistence, its paradox, its refusal to die, there is meaning. Not all particles are real, but all of them reveal. Even before tachyons had a name, they had a mythology. Because the moment science posits a thing that might move faster than light, that might travel backward through time, that might rewrite causality itself, it doesn't just stay in the laboratory. It escapes. It seeps into culture, into fiction, into the language of gods and ghosts and futures that come too soon. Tachyons have become something more than theoretical particles. They've become symbols, shortcuts for impossibility, for mystery, for the edge of what can be known. In Star Trek, tachyons are the currency of time travel, cloaking fields, and subspace communication. In Watchmen, they obscure visions of the future, clouding even the perception of a godlike being. In Doctor Who, they drift casually through storylines as explanations for paradoxes and cracks in time. To the casual viewer, the word tachyon doesn't describe a real thing. It represents something we're not supposed to understand yet, something too advanced, too strange, too fast for explanation. And maybe that's why the word stuck, because even in physics it was never just about particles. It was about what lies beyond the light, not in distance, but in principle. Tachyons in fiction and in theory embody the same idea, that the universe has layers we haven't yet peeled back. Science fiction didn't invent tachyons, but it gave them life. It gave them weight, not in mass but in meaning. It allowed them to exist in worlds where rules could bend, where timelines could fracture, where the past could be rewritten from the future. And in doing so, it gave us a language for the impossible. This isn't new. Science has always bled into story, and story into science. Long before we sent rockets to the moon, we wrote tales about it. Long before we split the atom, we imagined energy too powerful to control. Fiction doesn't just mirror science, it often precedes it. But with tachyons, something stranger happened. They became fictionalized before they were ever real. They entered the cultural bloodstream not as discoveries, but as metaphors. Tools for storytelling, shorthand for uncertainty. And in that way, they became more than science. They became part of our mythos. Tachyons tap into something ancient, our longing to defeat time, to unbreak the glass, to send warnings back to the moment before everything went wrong. They give shape to a very human hunger, the desire to bend reality into something more forgiving. In physics, tachyons raise questions about causality, about energy, about the very shape of space-time. In fiction, they raise hope, the hope that the future isn't fixed, that the past isn't unreachable, that something, some particle, some message, some version of ourselves might find its way across the great divide and make things different, better. It's no coincidence that so many of the stories that invoke tachyons are stories of regret, of lost chances, of timelines unwound and rewritten. Because we know deep down that time doesn't negotiate. It doesn't reverse, it only marches forward. Unless there's a glitch, a breach, a particle that moves faster than the moment itself. That's the power of the idea. Not that it's true, but that it might be. That it's perched on the edge of possibility, scientific enough to sound credible, wild enough to spark wonder. And so the tachyon has become a totem, a word that means more than it says. A vessel into which we've poured our fascination with the frontier, the space between the known and the not yet understood. It's easy to scoff at that, to say that science should be clean, that theory should stay theory and fiction should stay fiction. But the truth is more tangled. The two feed each other, always have, always will. Many physicists of the last century grew up on pulp science fiction, tales of warp drives and wormholes, tachyons and telepathy. Those stories shaped the questions they would later ask in earnest. And sometimes fiction asks the questions theory hasn't yet found the math for. Tachyons, in this sense, are perfect bridges. They exist in both worlds. In one, they're mathematical constructs, unstable modes in a vacuum, complex solutions in relativistic equations. In the other, they're story fuel, time messengers, plot pivots, deus ex machina wrapped in particles that never quite resolve. And standing between those worlds is us, the viewer, the reader, the thinker who wonders, could that ever be real? That question is more powerful than any answer, because it opens a door, not just to the science, but to the mystery behind it. The kind of mystery that built the Large Hadron Collider, that pointed telescopes at empty space, that spent decades chasing a massless neutrino or a Higgs boson or gravitational waves rippling from a collision billions of years ago. Science begins with story, with questions so strange they don't sound scientific, until they do. And maybe that's the real lesson of the tachyon, not that it exists, but that it's thinkable, and that we, as a species, are capable of entertaining such an idea, not to prove it but to see where it leads. That's what drives the best science, not certainty, curiosity, and sometimes the idea that first appeared as fiction circles back and lands in a detector, in a signal, in a theory that reshapes our world. Tachyons haven't done that yet. But they've done something else. They've kept the question alive, the one that all great science and great fiction quietly ask: what if the universe is even stranger than we imagine? And what if we're just beginning to catch up? There's a question physicists rarely ask out loud, but it lingers in the background of every theory, every experiment. What is the universe hiding from us? We think of reality as open, something we can explore, measure, decode, and in many ways it is. We've unlocked secrets from the smallest quarks to the largest galaxies. We've rewritten laws that once seemed untouchable. We've mapped the microwave afterglow of creation itself. But still, there are places where the map ends. Not because we haven't looked, but because something resists being seen. Tachyons are one of those resistances, not just because they move faster than light, not just because they defy causality, but because their existence, if confirmed, would crack open the framework we've spent a century building. And maybe that's why the universe remains silent. Not because tachyons don't exist, but because their discovery would be too disruptive. There are moments in science where discovery feels less like revelation and more like detonation, where a single observation threatens to unravel the scaffolding we use to understand everything else. The shift from Newton to Einstein, the collapse of determinism under quantum theory, the acceleration of the universe's expansion, defying all prior expectations. Each time, the discovery didn't just add something new, it demanded that we rebuild the foundation. A real, detectable tachyon would do the same, because it wouldn't just be a new particle, it would be an escapee, a violation of the cosmic speed limit, a brute force challenge to special relativity, to causality, to every light cone diagram ever drawn on a chalkboard. And yet, the equations have made room for them, which means either the math is wrong or we're missing something profound. Perhaps the silence isn't accidental. Perhaps the universe has firewalls, not of code, but of principle. Barriers that ensure certain kinds of information stay sealed away, not because they can't be known, but because they shouldn't. There are theories that suggest the laws of physics are self-consistent by design, that paradoxes are impossible, not just practically, but fundamentally, that any system threatening causality is automatically suppressed by deeper symmetries. This is sometimes called cosmic censorship, a principle that prevents us from seeing naked singularities or from constructing situations that break the causal order of events. It's not a law, per se. It's a philosophical safeguard, a kind of metaphysical immune system. And in this view, tachyons might be immune reactions, mathematical warnings that you've stepped outside the viable bounds of theory. They show up not to be confirmed, but to be redirected, reinterpreted into something consistent, something safer. Or maybe, more chilling still, they represent a kind of prohibited knowledge. Not in the mystical sense, but in the structural one. The idea that some configurations of the universe are unreachable by design, that there are truths which, if exposed, would unravel the logic of time itself. It's not a comforting thought. We like to imagine that with enough effort, enough precision, enough particle collisions, we can see everything, know everything, measure the unmeasurable. But tachyons raise the possibility that some truths run faster than our questions, that some phenomena are ontologically evasive, built to outrun detection, to stay just out of causal reach. This doesn't mean they're meaningless. It means they exist in a different domain, one that intersects with ours only through hints, through instability, through shadow. And maybe that's the point. Maybe the role of the tachyon isn't to be found. It's to challenge the idea that everything can be found, to force us to reckon with the possibility that reality is not entirely for us. It's an old idea, hidden beneath newer theories, that the universe is not required to be legible, that our instruments might be limited not by engineering but by structure. We build better detectors, we run larger colliders, we extend our equations to higher dimensions. And yet something remains missing, not just tachyons, but access. We sense it when we calculate things that break down at Planck scales, when we try to merge gravity with quantum mechanics and find infinities staring back. When the vacuum isn't stable but metastable, balanced precariously in a valley it could one day fall out of. These aren't gaps in understanding. They're pressure points, places where the physics groans under its own weight. Tachyons haunt those points, not as answers but as provocations. What if they're invisible by intention? What if they can never be slowed, never be seen, because their role was to stir, not stay? To shake the early universe, to sculpt the geometry of dimensions, to spark symmetry breaking, then disappear into silence, like flint to fire. It would explain their consistency in theory and their absence in observation. And it would also suggest something deeper, that the universe is not a machine, but a story, one written with tension and transition, with laws that flex just enough to birth form but snap back to prevent collapse. And in that story, tachyons are not errors. They're editor's notes, margins scratched with the warning, not here, not yet, not like this. The question then is not whether tachyons are real, but whether reality ever intended for us to catch them. And if it didn't, what else is it keeping just beyond reach? Imagine receiving a message before it was ever sent. Not an echo from the past, but a signal from the future, arriving fully formed as if time itself had folded in on you. No sender, no origin, just a truth that appears before its cause and dares you to ask, how? This is the haunting promise of the tachyon, not just motion faster than light, but information faster than time. A loophole in causality, a thread pulled from the wrong end of the timeline. Theoretical physicists call this the tachyonic anti-telephone, a thought experiment so disturbing in its implications, it's treated less as science and more like a warning. Two observers, moving relative to each other, equipped with tachyon transmitters. One sends a message,
The other receives it before it was sent. Each, in their own frame of reference, obeys the rules. Neither breaks causality, and yet the result is unmistakable. A closed causal loop, a paradox. In this loop, a message exists because it was received, not because it was created. There is no beginning, no true cause, just an effect chasing its own tail through time. What do we do with such a possibility? We deny it. We build frameworks to contain it. We construct arguments and reinterpretations to avoid it. We say tachyons, if they exist, must be incapable of carrying information, that they cannot be controlled, that they are inherently random, that any attempt to build a tachyon-based communication system would unravel under its own contradictions. And yet, the door remains ajar. The anti-telephone may be an impossibility, but the idea it reveals, that information could transcend time, is not so easily dismissed. We already know the universe is stranger than it should be. Quantum entanglement allows particles to correlate instantaneously across distances too great for light to cross in time. Quantum tunneling defies barriers. Virtual particles flicker in and out of existence, borrowing energy from the void and returning it before causality can object. We don't fully understand these phenomena, but we know they exist. Could tachyons be another such phenomenon? One we've only begun to glimpse. Some physicists have speculated that tachyon-like particles might appear in emergent time models, frameworks in which time is not fundamental but arises from deeper, timeless processes. In these models, the flow of time, the direction of causality, even the arrow of entropy, are illusions of perspective. And if that's true, then the rules that ban tachyons from our reality might not be absolute. They might simply be local conditions, laws that apply here, now, under our particular vacuum, but which could be violated elsewhere. It's a dangerous line of thought, because if information can move backward in time, if tachyons can transmit messages to the past, then the very structure of history becomes malleable, consequence becomes a negotiation, memory becomes mutable. And yet, we crave it. The ability to send a warning, to undo a mistake, to tell your past self what you didn't know when it mattered most. This is why the idea endures, not just in physics, but in culture. Tachyons have appeared in novels, games, films, as the delivery mechanism for foresight, for knowledge that shouldn't exist yet. In every story, they symbolize hope, or control, or despair, the power to change what was. But real physics doesn't care about drama, it cares about consistency. And consistency demands that tachyons, if they exist, must remain untouchable. You can't control them, you can't shape them, you can't build a circuit or a beacon or a transmitter. Because the moment you could, causality would collapse, not just in one moment but everywhere. And so if tachyons are real, the universe must protect itself from them. The laws must tangle their paths, cloud their intentions, bury their origins in noise and indeterminacy. But what if the protection isn't perfect? What if, under extreme conditions, in the early universe, in the quantum foam, in black hole event horizons, tachyon-like effects can slip through? What if certain events, certain signals, certain anomalies we've already recorded are, in some way, echoes from the future? We wouldn't know how to interpret them. Because every equation we trust begins with the assumption that time flows forward. But what if that's a choice? A symmetry, broken long ago, that made entropy increase in one direction instead of the other? What if another kind of physics, a mirror version, still exists, hidden in the folds of higher dimensions or buried under layers of quantum indeterminacy? In that version, tachyons wouldn't be forbidden. They'd be normal. And maybe, from their perspective, we are the strange ones. Slower than light creatures trapped in a single direction of time, blind to everything that moves the other way. Maybe we're not just missing tachyons. Maybe we're surrounded by them. Maybe they aren't particles at all, but patterns. Effects that precede causes, probabilities that push on the present before we even know what choice we've made.
And if that's true, then causality is not a wall, it's a veil, and tachyons are the shadows that flicker on the other side. We try not to look. We bury them in math. We dismiss them as artifacts, but they remain. Because we are not just creatures of the now, we are echoes of the future, shaped by the past, caught in a current we still don't understand. And the tachyon, it may be the ripple that tells us there is something waiting ahead. And it's already reached back. Stand still long enough in the dark, and your eyes begin to adjust. You start to notice shapes where before there was only black, the faint glint of structure, the suggestion of motion, something brushing just beyond the edge of perception. You don't see it clearly, but you know it's there. This is what tachyons have become, not discoveries, not data points, but contours in the dark, outlines of a reality that hasn't fully resolved, and maybe never will. We began this journey asking whether tachyons were real, and now, here at the edge of that question, we find something more profound, a reflection of how we define reality at all. Because in science, we rely on observation, confirmation, measurement. A thing is real when we can point to it, quantify it, predict it, and observe it behaving in ways our models can describe. But what about the things that shape our theories from the outside? What about the ghosts in the math? What about the solutions we discard? Not because they're incorrect, but because they don't fit. Because they move too fast or too strangely or too far beyond the reach of any detector we'll ever build. Do they exist? Are they real? Or are they simply artifacts of language? A language we haven't finished learning. Tachyons might be such artifacts, not errors but symptoms, not anomalies but indicators that something bigger is hiding behind the rules we trust. There are precedents for this. Virtual particles are never observed directly, yet they are essential in quantum theory. Ghosts that influence outcomes, that create pressure in a vacuum, that bend probabilities in measurable ways. The wave function in quantum mechanics is not real in the traditional sense. It's a tool, a map of possibility. Collapse it and reality snaps into place. But before that, it is an ocean of outcomes, none of them real, and yet all of them necessary. Tachyons may fall into that same category. They do not collide, they do not decay, they do not leave trails in chambers or ripples in space-time. But they matter because the equations don't fully make sense without them. They are the negative space in the portrait, the silence between notes that gives music its shape, the absence that defines the presence. And maybe that's what the universe is trying to show us. That not everything worth knowing can be held, not everything worth studying can be detected. Some truths exist only as boundaries, edges that tell us where our understanding ends. In this view, tachyons are not failures of physics. They are its horizon. They are what happen when you push a model too far, when you stretch a symmetry until it snaps, when you allow the math to ask questions your instruments can't. They are the echoes of every untestable truth, the possibility that time itself is reversible in some deeper sense. That causality is not absolute. That reality contains layers we are not equipped to experience, not yet. Or maybe ever. That's the hardest part to accept. That there may be truths we are not just unready for, but incapable of grasping. Not because we are small or primitive or not smart enough, but because we are local. We are embedded in one thread of a vast, tangled weave. We measure what crosses our thread and call that reality. But what if other threads pass near us without ever intersecting? What if tachyons live on such threads? Unreachable, invisible, not unimportant but orthogonal to our experience, real but from a vantage point we'll never hold. It's a sobering thought, but also liberating, because it reminds us that the universe is bigger than us, not just in scale but in structure, that there are truths we may never prove and yet are still worth contemplating. Tachyons, then, are not about confirmation, they are about invitation. They invite us to think beyond limits, beyond light, beyond time, to imagine what it would mean if the future could touch the past, if speed were not bounded, if cause and effect were not a line but a loop. And in imagining that, we begin to glimpse something rare in science. Not just knowledge, but awe. Awe that the universe could contain such possibilities. Awe that our minds can reach toward them. Awe that even in absence there is meaning. The tachyon is that absence, that whisper, that impossible thing that somehow still fits. And maybe that's all the answer we'll ever get. Not proof, not detection, just the deep, resonant hum of a universe that refuses to be fully known. And the question that hum leaves behind, lingering like a ripple through time. If tachyons aren't real in the way we understand reality, then what else might be moving through this cosmos and just out of reach? They told us the universe had a speed limit, that nothing could move faster than light, that time must always flow forward, that the structure of causality was immutable, etched into the very bones of space-time. But perhaps it was only a rule within the frame, a law that holds true here, now, for us, but not everywhere. Because lurking in the equations, shimmering just beyond detectability, is something that defies that limit. A whisper of speed beyond speed, a particle born not of motion, but of impossibility itself. The tachyon. It may never appear in a cloud chamber. It may never light up a detector or bend a magnetic field. We may never see it arrive, because it may already have come and gone, racing through time before we even knew how to measure. But its absence is not emptiness. It's an invitation to question everything we thought was unshakable. To ask, is time truly one-directional? Is light truly the boundary? Or are these just local truths, useful, familiar, but incomplete? We've seen it before. The Earth once felt flat beneath our feet, the sky, a dome, the atom, indivisible, and each time what we thought was the whole story was only the introduction. So perhaps the tachyon isn't a particle but a placeholder, a symbol for every frontier we haven't crossed yet, for every symmetry we haven't broken, for every question we're not yet ready or able to ask. Maybe that's why it's never been seen, because it was never meant to be, because its purpose wasn't to be found, but to make us search. The tachyon reminds us that physics doesn't just describe reality, it negotiates with it. It tests the seams, it tugs at the constants, it pushes against the edge of what's possible, not always to prove, but sometimes just to wonder. And in that wondering, something powerful happens. We become more than observers, we become participants in a dialogue with the unknown, not because we have answers, but because we dare to ask better questions. Are tachyons even real? It's tempting to say no, to close the book, to fold the equations neatly, to return to what can be seen and touched and measured. But something resists. A flicker in the math, a silence that echoes, a trace in the structure of the universe that says, "You've come far, but you're not finished." Not all truths arrive as facts. Some arrive as myths, as metaphors buried in particles, as paradoxes carved into time, as riddles too fast for causality to catch, and so the tachyon remains. Not because it exists in space, but because it exists in thought. It is what waits on the far side of knowledge, what outruns our instruments but not our imagination, what bends the arc of science just slightly toward mystery. And maybe that's the point, not to find it, but to know that something might still be running, faster than light, faster than thought, just out of reach. Not to be caught, but to remind us. The universe is not only more vast than we imagine, it is more vast than we can. Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.